Hey folks, what's going on? It's Mr. Murray coming to you with a little video here on tangent and circumscribed angles. Now in the textbook that we're using, Integrated Math 2, this is going to be section 19.3. Right, students in my course 2 honors class 2019-2020, you should have received through my.hrw.com, you should have received an interactive student lesson that's optional, but which I encourage you to look through. That's going to discuss a lot of the stuff that's going to be in the video. But the purpose of the video is just to give you a quick breakdown of some of the important ideas here. So I'm going to talk about what are tangent lines, what are inscribed angles, what are tangent angles, stuff like that. Okay, so to get started off, let's talk about what's a tangent and what's a tangent, what's a circumscribed angle, etc. So a tangent line is any line that comes through and touches the circle at just one point. Here's another example of a tangent line, and you have the one that's shown there. So tangent lines come by and they touch the circle at one point. Okay, so a line that intersects a circle at one point. Okay, now here a circumscribed angle, in this case is the intersection, or I would say a circumscribed angle is any angle whose vertex is outside the circle. So usually, right, remember we talked about inscribed. So an inscribed angle would have a point that's within the circle or that's on the circle, like this. This would be like an inscribed angle right here. Or if I wanted to connect the 2 points that I have, this would be an example of an inscribed angle. Okay, whereas this would be an example of a circumscribed angle. Okay, sometimes they don't necessarily have to be the intersection. Sometimes it represents, so this is notice the intersection of 2 tangent lines, right? So we have 2 tangent lines, they intersect outside of the circle, and that point of intersection forms the vertex of the circumscribed angle. And then the 2 points of, these are what we call points of tangency, the point at which that one point where the line touches the circle, right? So the points of tangency here, right, give us the ACB or the BCA, that circumscribed angle. Okay, so in this video, again, we're going to be diving a little bit more into what are tangent and circumscribed angles, what are things we know about them, what are things we can do with them. Please note that this lesson may make use of inscribed angles or quadrilaterals, whether that be proving things or whether that be in actual exercises. The stuff we've learned is going to keep coming back and being built on. All right, so the first main thing we know is this, and this might have seemed kind of potentially obvious based on what you're seeing with these tangents here, but if a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency. In other words, what that means is that the point where the line hits this radius that connects the circle to the point of tangency, you're always going to have a 90-degree angle. So for example, if I was asked, what is OXY? The measurement of OXY is 90 degrees, because that is the point, X is the point where the tangent line hits the circle. So this radius connecting the center to X must be perpendicular, form a 90-degree angle with the tangent line. What if I want to know what R was? Well, I could figure that out by noting that this is the radius and this is the tangent line. So this is 90 degrees. Then I take 90 and I add 61, and that gets me 151. And so what that tells me is, in order for this to be a triangle, R needs to be 27 degrees. so that all three angles are not 27, I apologize, 29 degrees. So all three angles will add up to 180, right? We get 151, 171, 180. Okay, so this is true. Whenever a tangent line touches the circle, it's perpendicular to that radius that connects the circle, the center, to that point of, remember, this is called, that point is called the point of tangency. Okay, you see that used right there. Okay, so that's something we need to know. Another thing we need to know is this: a circumscribed angle of a circle and its associated central angle are supplementary. Let's take a second to unpack that. So we have a circumscribed angle, and forgive me on the colors there, an associated central angle. Okay, I'll do it here too. This would be our center, and this would be, so what it's saying is, so we have a circumscribed angle, right? Now, that circumscribed angle has to do with right intersection points here, right? Sorry, I think my pad kind of had a little bit of a freak out there. So in any case, what we know is that these are supplementary. And if you want to know, let's think about why. Well, take a look. Now, we're assuming that this circumscribed angle has to do with the intersection of tangent lines. For I've seen it defined as not necessarily being tangent lines, but assuming that we define it as these have to be tangents, and this is an intersection of tangents, well, from what we just talked about, this has to be 90 and this has to be 90, right? So what we have is, think about it like this. We have 90 degrees plus 90 degrees, right? Plus 37 degrees plus whatever this is. So RQS has to be equal to 360 because it's a quadrilateral, right? There's four sides, and any shape with four sides has to have interior angles that add up to 360. So if we do some math and take a look at what if we were to eliminate 90 and 90, and by subtracting them on both sides, well, you see what you get is 37 plus m of RQS is equal to 180. And by definition, that means these are supplementary. And then, of course, you could solve, and you could see that the measurement of Q has to be equal to 143 degrees. So when you add 37, rather, right, you get 143 plus 37, which is 180. Now, we can show that it doesn't just work with when you have numbers. Let's say this was x and 3x. So again, because these are tangents, what we know is that at the point it hits the circle, it's going to be perpendicular to these radii, right? We know these are radii. So essentially, we know that x plus 3x plus 90 plus 90 equals 360. Okay, and by the same logic as the red over there, we get x plus 3x is equal to 180. So again, that shows you that the circumscribed angle and the central angle are always supplementary. And then you can solve this to get 4x equals 180. So x equals 45 degrees. And you get 45 and 135. Okay, so that is an important theorem, right? Whenever you have a circumscribed angle, if you can find this, but it goes further, because remember that this central angle is always congruent to the arc. So not only that, but you could also say the associated arc. So not only the associated angle, but the associated arc are also supplementary, because if x and 3x are supplementary, and 3x is the congruent to the arc, then x and the arc also have to be supplementary. Okay? Another thing that we need to know is about the tangent congruency theorem. And what this says is that if we have two tangent lines, okay, to a circle that originate at the same point, those lines will always be congruent. Now, if we define a secant such that a secant always has to do with a tangent, right? It always is touching at the tangent, right? Or rather, if not a secant, if we define, rather, I apologize, if we defined a circumscribed angle as an angle such that it always involves two tangents, okay, then that means if we define it this way, then these will always be congruent to one another. So for example, 3x squared is equal to 18x. So x squared is equal to 6x divided by 3. So x squared minus 6x is 0. So x times x minus 6 is 0. So either x is 6 or x is 0, but there's a 0 length wouldn't really make sense here. So x is 6, and you can see plugging in, if you were to do 18 times 6, right? Like if you were to plug it into your calculator, you would get, I believe, 108. I'll do that real quick. 18 times 6 equals 108. Yep. And then if you do 6 to the power of 2 times 3, you also get 108. So you can see the lengths are equal. Nice. Over here, you can see a similar thing. 2x squared is equal to, rather, 10x. So you divide, and you get x squared is 5x. You subtract the 5x. You factor out the x. And then you solve. X is 0 or x is 5. But it can't be 0, so it must be 5. And if you plug in, you'll see both lengths are 50. Okay, so these are the three big things you need to know about tangents and circumscribed angles. 1, a tangent is always perpendicular to the radius connecting the center to the point of tangency, the point at which the tangent touches the line. The circle, rather, the point at which the tangent touches the circle. 2, a circumscribed angle of a circle and its associated central angle and arc are supplementary. That is to say, this measurement of the circumscribed angle is always this plus the center adds up to 180, the central angle, okay? And then this plus the arc also has to add up to 180 because the arc is congruent to the central angle. And lastly, two tangent lines originating at the same point are congruent, meaning that the two sides of this angle have equal length. Okay, so I'm going to move on, and this is going to be an opportunity for you to try some problems. So what I want you to do is take a look at the situation. We have a circumscribed angle sitting outside, and that's measuring in at 40 degrees. What we need to do is we need to do this. We need to find the measurement of BAD. Well, we have BAD, that's 40. We need to find ABC, so you need to find this whole angle here. Okay, we need to find DCB, this little angle here. Note the order is very important. We need to find BDA, this little angle here, and then we need to find CDB, this little angle right here. Okay, so here's what I want you to do. I want you to take a moment. I want you to pause the video, try to find these 4 angle measurements, and then when you're ready, unpause, and you can see what I got. Okay, so let's jump into it. Let's start with ABC. So look, ABC, well, notice BC is a radius. AB is a tangent line. This radius and this tangent line must be perpendicular. So that would have to be 90 degrees. The whole thing is 90. Okay, so this little piece plus that little sliver are 90. So it's not, we don't know really enough information right now. DCB. Well, remember, we know that the measurement of this has to be supplementary with the measurement of this. So if this is 40, then DCB needs to be 140 in order for them to be supplementary. Now, I'm going to do this out of order because I'm not sure necessarily off the bat. I'm sure there is a way, but I'm struggling with how I'd find BDA. But if you notice, well, observe how this and this are both radii, right, of the same circle. So if radii of the same circle are congruent, that's a fact, then this is an isosceles triangle. And if this is an isosceles triangle, then this little sliver and this little sliver are equal to each other. And if that little sliver and that little sliver are equal to each other, we can figure out stuff from there. Here's another thing I just noticed, though. Remember that these two lengths have to be equal. So that means, right, this length and this length are congruent. So this base angle and this base angle are also congruent. And so basically, if this is 40 degrees, then these need to be 140 in total so that all three triangle angles add up to 180. So I basically have two of the same angle is equal to 140, so each angle is equal to 70. So that should mean the black angles are each equal to 20 rather, so they add up to 90. Let's see what happens if we'd done it the other way. So this is 140, so I've got 2x. Now if this is 140, the remaining angles have to add up to 40. So I get 140 plus 40 equals 180 because it's a triangle. So notice x equals 20. So there's, again, two ways you can do this. Let me just fill this in. So BDA equals 70 and CDB equals 20. So the first thing I did is I said, well, look, because these are both tangents that meet at the same point, these lengths must be equal. Because these lengths are equal, this is an isosceles triangle. Because it's an isosceles triangle, in a sense, and because these are equal, these opposite angles are also equal in measurement. Now, since this measurement is 40, that means that these need to add up to 140. So you get 140 plus 40 equals 180. And if they have to add up to 140 and each of them are the same, then each has to be 70. And this equation shows that. Alternatively, we have the same thing here. Because these are radii of the same circle, they must be congruent. All right, again, we get an isosceles triangle and congruent base angles. Because this angle is 140, these have to be 40 together. So we get 40 plus 140 equals 180. And if they're the same, each of them needs to be 20. So we get 20 plus 20 plus 140 equals 80. So please make sure you understood that. If needed, rewind. And then in a couple seconds, I'll move on to the last U-try. All right, last one, refer to the figure here. AB is tangent, so we got a tangent line. AD is also tangent, and they're intersecting outside at that point A. Determine each of the given angle measures. We need BCD, CDA, BED, and DBA. Now, as I suggested in the last problem, you can do them in order, 5, 6, 7, 8, and they'll each kind of feed into each other. Or if there's a better order you can do them in, feel free to go ahead. Don't feel that you need to go 5, 6, 7, 8 unless you actually need the information from the previous number. All right, so again, please go ahead, pause the video, try to get these 4 angle measurements, and then when you're ready, unpause, and you can see what I got. Okay, so BCD, that's the center of the circle, right? So what we know is that 32 degrees plus the measurement of BCD is 180 because they have to be supplementary. And so I subtract 32 degrees on both sides, and I get 148 degrees. Okay, CDA. Well, CD is a radius. DA is a tangent, so therefore they must be perpendicular and meet at a 90-degree angle. BED, this is a circumscribed angle. Not a circumscribed, I apologize, an inscribed angle. So this angle must be half the measurement of the corresponding central angle, and if the corresponding central angle is 48, then this needs to be 74. Because it's got to be half the measurement of the corresponding central angle. And finally, DBA. So I want this little piece right here. That's going to be pretty challenging, but let's see what we can do. Again, observe how because of these being tangents, okay, we know that these are going to be equal because two tangents that meet at the same exterior point are going to be congruent to each other, so they'll have equal length. And so therefore, these base angles will also be congruent. So I've got 32. Let's say that each of them are equal to x degrees. So I've got 32 plus 2x degrees equals 180 due to the triangle angle sum theorem. So when I subtract 32 and I get 2x equals 148, as we've seen before. And then I divide by 2, and x is equal to 74 degrees. All right. And so that's the idea there. Now, the other way we could have done it is like this. Again, these are two radii of the same circle, so these base angles must be equal. Since BCD is 148, these must each be 32, or they have to add up to 32. So each of them need to be 16. But then because this has to add up to 90, if this is 16 and these need to add up to 90, the other piece has to be 74, aka 90 minus 16. All right, so hopefully this video made sense and was helpful to you. I do have a quick 5-question maya.hrw.com activity on tangent and circumscribed angles. But best of luck, keep it up, and remember, you can do it. All right, that's all for now. Please feel free to subscribe for the latest videos, and have a wonderful day.